matching networks, and we're going to do some better work on them now that we have all this knowledge of second-order systems. Specifically, we're going to tackle the challenge of building a matching network for Rn values that aren't equal to 1. We're splitting up that task into two parts. We're going to get a conceptual idea of how our matching networks work in this video, and then we'll come up with design equations in the next video. This is a copy of our matching network schematic. Up until now we've put single reactive elements in the matching network box, and we found that lets us cancel out reactance and susceptance that's in the load. We called that strategy ringing out the reactance because it worked at resonance, but it only worked if the resistance of the load was already Z0. Today we're going to try to deal with the situation depicted here where the load is not Z0. Our secret weapon for approaching this problem is the series to parallel transform, because we observed that it made resistances look bigger or smaller, which reflects the underlying reality that currents or voltages in reactive parts of an RLC circuit get amplified by Q. One tempting way to make this matching network is by just putting a resistor in the matching network box. You could add a series resistor if the load is less than Z0, or a parallel resistor if it's greater, as in this case. While this can guarantee the transmission line sees Z0, it forms a voltage or current divider that takes power away from the load. That's a really bad strategy in many high-speed applications for two reasons. Delivering power to the load is important, and power is often scarce because of attenuation and reflections. However, one silver lining to this type of match is that it works at any frequency. As a result, you might sometimes use this matching network if you were trying to stabilize a very touchy amplifier that really needed to see 50 ohms at every frequency. Instead of adding a lossy resistor to change our apparent resistance, we're going to add a lossless LC network. I'm going to depict that process on Smith charts as we construct the network at the bottom of the page. We start by depicting our load, which is at some real point other than the origin. Then this shunt capacitance adds some susceptance to our load. Notice that we've switched over to admittance axes so that we can easily move along lines of constant conductance as we add this susceptance. We arrange for the susceptance to carry us to the point where the line of constant conductance intersects with the Rn=1 line of constant resistance, which you can see faintly in the background of the plot. Finally, we switch back to impedance axes and note that our load just looks like Rn=1 plus some negative reactance. We add some series inductance to cancel out the negative reactance and wind up at the origin, perfectly matched. This type of LC network is called an L-match because it kind of looks like the letter L if you turn your head sideways right here. That's an L. Notice that L-matches only work at one frequency because the exact amount of susceptance and reactance that we add with the shunt cap and series inductor changes with frequency. There are four different types of L-matches, and I'm going to show those matches and their effect on Smith charts on this slide. We've gotten started with one familiar L-match on top here, and one new one on the bottom. The new L-match on the bottom is the same as the one on the top, except that the inductor and the capacitor positions have been switched, and you can see that the circuit has the same net effect as the L-match on the top. It results in the same load impedance, so this normalized resistance of 2 being transformed down to the characteristic impedance of Z0. The only difference between the two Smith chart is whether the L-match creates a negative reactance or a positive reactance with the first shunt component, which changes whether the arrows on the Smith chart point up or down first. Both of these networks transform a high load impedance to a lower value of Z0. And one handy way to remember that these networks transform down is thinking about whether you'd analyze them with a parallel to series transform or a series to parallel transform. You'd analyze these two by using a parallel to series transformation to create a series RLC circuit. And you can remember that the series resistor is always smaller than the parallel resistor in a transform, so this arrangement of components must reduce the apparent resistance. You can also turn the letter L backwards to make circuits in this column. Here we have to perform a series to parallel transform in order to make these networks into easy-to-analyze parallel RLC circuits, and that'll result in the resistance of the network appearing higher than the resistance of the load. Let's focus on the upper right circuit and Smith chart pair to talk through an example of how resistance gets transformed upward on a Smith chart. Here the series capacitor results in a negative reactance, so we move down from our Rn equals 0.5 point along a circle of constant resistance. And that puts us on the Gn is equal to 1 admittance circle. Then we add a negative susceptance of a shunt inductor to shift us up that Gn equals 1 circle to the origin along there. Finally, we have to confront the fact that the circuits in the top row seem to do the same thing as the circuits in the bottom row. That's true, and so we pick between these rows for mundane reasons. The top row components will be differently sized than the bottom row, so they may be easier to build. For instance, big inductors are hard to make. Also, sometimes the parasitics in our circuits will be easy to merge into either the top or the bottom row. A classic example is that amplifiers always have some shunt capacitance. So this upper left matching network with a shunt capacitance in parallel with a termination resistance is often easy to build, because we get some capacitance for free. So in summary, series or parallel resistors in matching networks waste incident power, and so we don't use them. L matches are made of a shunt and a series inductor and capacitor, and they can match R values that aren't Z0. And there are 4 types of L match networks. There are L match networks that step the load impedance down, and you can recognize those because they need to undergo a series to parallel transform. There are also matches that step the impedance up, and you can recognize those because they need to undergo a parallel to series transform. And finally, you can pick whether you're using a shunt inductor or a shunt capacitor based on parasitics and component values.